Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Module 047, Feedback Oscillators. Please follow me in the Engineering Lecture Series by subscribing to my YouTube channel at https://youtube.com/@ndinechi-michael-c. Like, share, and drop your comments in the comment section or reach out to me using my email addresses. Listen to related lectures on oscillators and diodes using the two links supplied. Also, if you visit Ebony Educational Consult website at www.ebonyeducationalconsult.com, you will get more lectures in engineering. Last time we treated oscillators in general. While we were treating oscillators, we said that two classes of oscillators exist. The first class is the one that employs feedback to operate, while the second version is what we call the relaxation oscillators. In the feedback type, we talked of some type of oscillators that employ RC, resistor-capacitor combination, to produce oscillation. And we said in that category, we have a good example, which is the Wien bridge oscillator. We quickly put that these Wien bridge oscillators, or the feedback oscillators, operate at frequencies below 1 megahertz. So in this lecture, we will use the Wien bridge oscillator to bring out what happens when we make use of RC as our oscillating portion of the oscillator. We will go ahead to also look at the ones that use L and C, inductor and capacitor, to produce oscillation. In that class, we'll be looking at the Colpitts Oscillator. Then we will quickly look at the ones that use voltage-controlled oscillators, VCO, in the feedback loop to produce oscillations. So let's quickly start with the Wien bridge oscillator. The Wien bridge oscillator is in the class of the sinusoidal feedback oscillators. A fundamental part of it is a lead-lag circuit, as shown in Fig 1a, which consists of resistor R1 and capacitor C1 in the lag portion, whereas resistor R2 and capacitor C2 form the lead portion. At low frequencies, the lead circuit takes over due to the high reactance of C2. As the frequency increases, this reactance of C2 decreases, thereby allowing the output voltage to increase. That is the typical circuit of the Wien bridge oscillator. If you look at it, you see where we marked with pink say that that circuit consists the lead lag circuit, while the one shaded dark represents the voltage divider of the circuit. The assumption is by now we know what voltage dividers do in any circuit. Help to reduce current or voltage going into the equipment they are meant to protect. So let's go on and explain what happens here. Be flipping back to that circuit as we explained. Now, at some specified frequency, the response of the lag circuit takes over, and the decreasing value of C1 reactance causes the output voltage to decrease. The response curve for the lead lag circuit is as shown in Fig 1b, we will see it, and indicates that the output voltage peaks at a frequency called the resonant frequency, denoted by F subscript R. At this point, the attenuation, that is V out over V in of the circuit, is 1 over 3 if R1 is equal to R2 and the reactance of C1 is equal to the reactance of C2. So mathematically, we can say that V out over V in is equal to 1 over 3. Attenuation means the ratio of the output to the input. We say it is very important point when it is 1 over 3. And that point happens when R1 is equal to R2 in the voltage divider section of that figure we've seen, and the reactance of C1 is equal to the reactance of C2. So the resonant frequency of the Wien bridge is therefore giving us F subscript R equals 1 over 2 pi RC. So if you look at that equation, you see that the only variable you can have there is the value of R and the value of C. And we know from what you have said, when R1 is equal to R2 and C1 is equal to C2, then the output ratio becomes 1 over 3. And it is that decrease in the output that is called attenuation, represented by letter beta. Now, if you look at Fig 1b, we see that this response we are seeing is of two sides. To the left, we have the leading side. Starting from 0, it continues to go up. At a point of reflection where you now mark as FR, the output voltage is 1 over 3 of the input. That is the attenuation. So at that point, you have a point of reflection and the lag takes over. So as the voltage output decreases, the frequency increases. So at the 0 mark, you have a curve like this. So if you repeat that, the leading edge will go up again and the lag will come down again. So you continue to have your oscillation taking place. In a circuit, in a plot like this, we say that the rising side is the leading side, while the dropping side is the lagging side. So you see that important thing comes up in this plot, that the leading circuit, as the voltage continues, the output will continue to rise at a point where it is exactly 1/3 of the input voltage. Then the lagging circuit takes over and the frequency continues to drop, or the value of the output continues to drop. At the point of 0, it forms a response as we plotted here in blue color. So you say at this point, note that the lead lag circuit in the Wien bridge oscillator has a resonant frequency denoted as Fr, at which the phase shift through the circuit is 0 degrees and the attenuation is 1/3. In our lecture on oscillations, we made it clear that for oscillation to take place, that the net phase shift must be equal to 0 degrees and that the attenuation must be the attenuation equal to 1/3, and at that point that attenuation is occurring, that the voltage gain will be equal to unity. Those were the two conditions. So we've seen that at the point where the net phase shift is equal to 0 is at the peak. At that point we have Fr, and on the V side we have it to be 1/3 Va. At that point of reflection, the net phase shift is equal to 0 degrees. Now, below that Fr, that is from Fr to your left, the lead circuit dominates and the output leads the input. So when the output leads the input, you see that the V out will continue to increase. Now, above Fr, that is the resonant frequency, the lag circuit dominates and the output lags the input. So it continues to decrease. Now, let's look at the operation of this Wien bridge. The lead lag circuit is used in the positive feedback loop of an operational amplifier, as we have seen in Fig 1a. A voltage divider, that is that R1, R2 portion marked in dark shade, is used in the negative feedback loop. Therefore, the Wien bridge is reviewed or viewed as a non-inverting amplifier. Put in the non-inverting configuration, with the input signal fed back from the output through the lead lag circuit. The lead lag circuit is the portion we marked in orange. Because the voltage divider determines the closed loop gain of the amplifier, we can now say mathematically that the ACL, that is the closed loop gain, is equal to 1/beta which is equal to 1 over that R1 and R2 in parallel. When we solve R1 and R2 in parallel, it will give us R1 plus R2 all over R2. That is from our basic circuit analysis. So we say that the voltage divider, which determines the loop gain of the amplifier, is given as a closed loop equals R1 plus R2 over R2. Now, what are the conditions for oscillation to take place? Like we have said before, the net phase shift must be equal to 0 degrees and the gain must be equal to unity. These are the conditions for oscillation to take place and be sustained. So say the 0 phase shift condition is met when the frequency is FR, because the phase shift through the lead lag circuit is 0 degrees and there is no inversion from the non-inverting input of the operational amplifier to the output. So that is why in that response plot, it is important to note the position of FR, that at that point, which mathematically we can say is the point of reflection, that the lead circuit and the lag circuit has 0 degree phase shift. So as conditions continue to change, then the plot continues the other way around. So this condition again is illustrated in Fig 2a. Now, for the gain around the feedback loop to be unity, it means then that the closed loop gain ACL of the feedback must be equal to 3. Remember, the attenuation V out over V in is equal to 1 over 3. So to make it unity, it means that the amplifier or the op amp must be able to amplify by 3 to nullify that attenuation 1 over 3. So we say that the closed loop gain of the amplifier must be equal to 3 for the gain to be unity, since the attenuation is 1 over 3. So if you look at that plot again, we still remain the same, but the lead lag circuit we have replaced with that block to show that what happens there in that lead lag circuit is that for oscillation to take place, the positive feedback loop phase shift must be equal to 0, and the attenuation, which is which happens as a result of the losses in the lead lag circuit, must be compensated by the amplifier or the amplifier gain being equal to 3. When it is equal to 3, then the losses in the lead lag circuit is compensated by the amplification by of the amplifier by 3. So say that this offsets the voltage gain in the loop or the closed loop voltage gain ACL. In order to offset this 1 over 3 attenuation of the lead lag circuit, must have a total of 3, so that the feedback loop gain must be equal to 1. And we say that this is achieved when R1 is equal to 2 times R2. We've seen R1, we've seen R2. So if you're using R1 5, then R2 must be 10. 5 kilo ohms, 10 kilo ohms. That is for this condition to be achieved. So that is what we're also saying here, that there's no difference. We've explained this. For the loop gain to be equal to 1, the closed loop gain or the amplifier must be able to amplify the signal by 3 times. So when that happens, the closed loop gain will be unity, that is equal to 1. Now, it's something we need you to do. Just show how oscillation startup occurs in the Wien bridge by using a suitable diagram. So we jump that, and while you do that at home, let us quickly look at oscillators with LC feedback. Wien bridge is a good example of oscillators that make use of RC. And in that group, we also have what we call the Hartley oscillators and the phase shift oscillators and the 20 oscillators. We have mentioned that in our previous lectures, that in the RC feedback oscillators, we have the Wien bridge, the 20, and some other ones, but the main one that's very good in using for illustration is the Wien bridge. Some people also use the phase shift to do that. But let's quickly look at oscillators with LC feedback loop. LC feedback elements are normally used in oscillators to achieve high frequencies of oscillation. We say RC is limited to below 1 megahertz, but the inductor capacitor element in the feedback can be used for higher frequencies of oscillation. Here, the transistors instead of operational amplifiers are used. Transistors like the bipolar junction transistors and field effect transistors are often used as the gain element instead of the operational amplifiers. Reason being that the frequency limitations of op-amp hampers achieving high frequencies. In one of my previous lectures, I've talked about the bipolar junction transistors, so you can refer to my lectures to know more about bipolar junction transistors. Then, in subsequent lectures, we will be treating field effect transistors. So at this point, I would like to ask you to subscribe to my YouTube channel so that when we treat these field effect transistors, you'll be able to, understand and follow. So in this class of LC oscillators, we have the Colpitts oscillator, the Hartley oscillator, the Colpitts oscillator, the Armstrong, and the crystal control oscillators. And often they are called resonance circuit feedback oscillators. So in this lecture, we will quickly look at the Colpitts oscillator as well as one of the crystal control oscillators. The Colpitts oscillator is shown in Fig 3. It uses an LC circuit in the feedback loop to provide the necessary phase shift and to act as a resonant filter that passes only the desired frequency of oscillation. Now, in electric circuits, we have what we call filters. Filters can be band-pass filters, they can be low-pass filters, they can be high-pass filters, they can be band-stop filters. So, but the important thing is that filters only allow designated frequencies to pass and reject by attenuating off all the unwanted frequency ranges. So this Colpitts oscillator say that provides the necessary phase shift and to act as resonant filters. That is, any circuit, any frequency that is not operating at the resonant frequency will not be allowed to pass. The approximate frequency of oscillation in the resonant frequency of the LC circuit is given by the values of C1, C2, and L. Remember, L represents the inductor, which is according to the formula F subscript R equals 1 over 2 pi square root LCT, where CT is the total capacitance in that circuit, which is equal to CT equals C1 C2 all over C1 plus C2. So this is a typical circuit of the Colpitts oscillator. Now, if you look at the area marked with red box, that is the feedback circuit. And in that feedback circuit, we have two arms. One arm is the inductor and the other arm is the capacitor. So it's a parallel circuit, so to say. Now, under normal conditions, C1 and C2 are assumed to be in series. That is why the C total is given as C1, C2 all over C1 plus C2 in the previous equation we have seen. Then the upper part, you can see, instead of using an operational amplifier now, we are using a bipolar junction transistor. And we say because the operational amplifier has some limitations in their frequency ranges, so as we expect higher frequency, we make use of bipolar junction transistor in this high frequency oscillator. Now, the condition for startup is that the attenuation beta of the resonance circuit, feedback circuit, is basically determined by the values of C1 and C2, as shown in figure 4. The figure there we repeated, but just using amplifier circuit or symbol to represent the amplifying side of figure 3, then redrawing that feedback circuit that contains C1, C2, and L. Now, if you look at this circuit, you see that the output voltage, V out, is what appears across C2, while the feedback voltage, Vf, is also what goes back to the amplifier. Because it's a feedback circuit, the feedback goes through the LC circuit, which is the feedback circuit, back to the amplifier, while at the same time giving an output. So both the phase shift to be equal to 0 and the gain to be unity all happens in this circuit we are seeing here before going back to the amplifier. Now, let's see what happens. The voltage developed across C2 is the oscillator's output voltage V out, and the voltage developed across C1 is the feedback voltage Vf. The expression for the attenuation, that is beta equals C2 over C1. Recall to say that the attenuation is the ratio of the output voltage to the input voltage. Now, the output voltage is developed across C2, while the feedback that goes back to the amplifier, which is the input, is developed across C1. So this beta attenuation is the ratio of C2 to C1. Now, for oscillation to be sustained, the voltage gain, AV, must be equal to 1 over beta. Therefore, this AV will be equal to C1 over C2 because the attenuation is 1 over beta, while beta is C2 over C1. So 1 over C2 over C1 automatically inverts C2 over C1 to mean C1 over C2. That is why we say that at that point our AV is equal to C1 over C2, where AV is the voltage gain of the amplifier. Then it is important here for us to note that, as we have stated earlier in our previous lecture, for the oscillator to be self-starting, the gain times the attenuation must not only be equal to 1, it must be greater than 1 for it to be self-starting. So when it starts, because the gain is more than 1, then the output increases in amplitude, is amplified, it continues until it gets to the point where you want. At that point, you do some modifications so that the output remains constant. In our previous lecture, we have done that plot where we say that at t equal to 0, then it continues to increase when AV is greater than C1 over C2. At the point where it gets to the frequency, the desired frequency, that is, you have to now clip it for AV to be equal to 1 so that the output frequency will now remain constant. So that is what happens in the Wien bridge. So we have seen that all the conditions for oscillation to take place in the LC feedback, the RC feedback is being met. The next class of oscillators using feedback mechanism is the crystal controlled oscillators. Say that these are the most stable type of feedback oscillators and use a piezoelectric crystal in the feedback loop to control the frequency. Of course, we know that quartz is a type of crystalline substance found in nature that exhibits this piezoelectric effect. This piezoelectric effect occurs when a changing mechanical stress is applied across the crystal to cause it to vibrate. A voltage then develops at the frequency of mechanical vibration. Conversely, When an AC voltage is applied across the crystal, it vibrates at the frequency of the applied voltage. The greatest vibration occurs at the crystal's natural resonance frequency, which is determined by the physical dimensions and by the way the crystal is cut. Crystals used in electronic applications typically consist of a quartz wafer and has a schematic symbol shown in Fig 5a. Of course, it has an electric equivalent circuit, which is shown in Fig 5b. As we can see from that figure, the crystal equivalent circuit is a series parallel RLC circuit and can operate in either series resonance or parallel resonance. You can see why we say that the VCOs, voltage control oscillators, are more stable because they combine the effect of RC and the effect of LC, resistor, capacitor, inductor, capacitor effect to produce oscillation in the feedback circuit. So this is the symbol. So any circuit you see that symbol, it means that it's talking about voltage control oscillators using quartz. It's feedback lead-lag circuit. If you look at Fig B, you see that it is, a parallel circuit. In one arm, you have the series RLC. In the other arm, you have the capacitor circuit, which is equivalent to RC because, their internal resistance, even though not represented, is always there. Now, at the series resonant frequency, the inductive reactance is cancelled by the reactance of CS. Let's go back a bit and look at this. If you look at this Fig 5b, you see on the right is where you have the RLC circuit or component in series. We say at that point, resonant point, the reactance of LS and that of CS from our basic circuit theory must be equal. So the developed voltage only appears across the series resonant frequency. The inductive reactance is cancelled by the capacitive reactance CS. The remaining series resistor RS determines the impedance of the crystal. And parallel resonance occurs when the inductive reactance and the reactance of the parallel capacitance CP are equal. I'm sure that my listeners must have treated in their basic electric circuit theory resonances. So when on the right hand of the circuit, the capacitive reactance CS and the inductive reactance are equal, then the voltage there only develops across R. Then it means that it is now R in parallel with the capacitor on the left side of the circuit, which is CP. So we say that when that two components are left, we now have what we call the parallel resonance. And this parallel resonance occurs when the inductive reactance and the reactance of the parallel capacitors are equal. The parallel resonant frequency is usually about 1 kilohertz higher than the series resonant frequency. So a great advantage of the crystal oscillator is that it now exhibits a very high Q. In resonance, what is important is the Q factor of the circuit. It is not for us to, treat here, but this analysis have shown why the voltage control oscillators using crystals like quartz are preferred in high frequency and very stable oscillators. Oscillation is needed. So with this, we try to conclude that the impedance of the crystal is minimum at the series resonant frequency, thereby providing maximum feedback. The crystal tuning capacitor is used to fine-tune the oscillator frequency. That is to make sure that the frequency is stable and, if I may use the word, pure. So as we go on, we will now move to our next lecture, which will be on relaxation oscillators that make use of things like 555 timers to, give oscillation, though for non-sinusoidal signals. So join us in the next lecture where we'll be looking at the relaxation oscillators. There you will now see how square wave, rectangular wave, and sawtooth waveforms are being generated by oscillators, which we'll be using the 555 timer to achieve. Thank you for listening. Thank you for your time. Once again, like, share, and subscribe so that you get subsequent notifications. Thank you.